Saturn may be the most beautiful planet in our solar system, but for humans, it could become the ultimate one-way journey. Behind its golden rings is a brutal reality, distances beyond anything we have conquered, radiation that never stops, a body slowly breaking down, and a destination with no solid ground to stand on. Even reaching Saturn would be a historic miracle. Surviving it would be something else entirely. And coming home may be the hardest part of all. Today we explore why anyone who goes to Saturn may never come back. Now, let's begin. Every single human being who has ever left Earth, every astronaut, every cosmonaut, from Yuri Gagarin's first orbit in 1961 to the crew living aboard the International Space Station right now, has never traveled more than 400,000 kilometers from home. 400,000 kilometers. That is the absolute outer edge of everything humanity has ever done in space, with human lives on board. Every mission, every record, every triumph of human courage and engineering, all of it, combined, fits within that boundary. Saturn is 1,200,000,000 kilometers away, not a little further, not the next step on a logical progression. 1,200,000,000 kilometers, which means Saturn sits 3,000 times farther away than the farthest any human being has ever gone. 3,000 times beyond the entire accumulated history of crewed spaceflight. That one number quietly dismantles an assumption most people carry without ever examining it. There's a belief that sounds completely reasonable on the surface: we went to the moon. Mars is next. Saturn is just the step after that. It feels like how progress works a ladder, one rung at a time, each achievement building naturally toward the next. It's the kind of thinking that makes space exploration feel inevitable, a matter of patience and willpower and sufficient budget. It is completely wrong about the scale involved. Going from the moon to Saturn is not climbing one more rung. It is the difference between stepping off your front porch and deciding to swim the Pacific Ocean. The moon sits at an average of 384,000 kilometers from Earth. Saturn, at its closest approach, sits at approximately 1,200,000,000 kilometers. When Saturn reaches the far side of its orbit, that number grows to over 1,600,000,000 kilometers. These are not comparable distances in any meaningful sense. They occupy entirely different categories of physical reality. And conflating them is the first mistake almost everyone makes when they imagine humanity's future in space. Here's a way to feel the difference viscerally. When NASA communicates with astronauts on the International Space Station, the radio signal travels at the speed of light, 300,000 kilometers per second, the absolute speed limit of the universe, and it arrives in approximately 1.3 seconds. You speak, they hear it in 1.3 seconds. It functions almost like a phone call with a minor delay. Send that same signal to Saturn. Traveling at the same 300,000 kilometers per second, that signal takes up to 83 minutes to arrive. One way. So if a catastrophic system failure occurs on a crewed Saturn mission, an explosion, a hull breach, a medical emergency, the crew transmits an alert. Earth receives it 83 minutes later. Earth responds instantly. The crew receives that response 83 minutes after that. 2 hours and 46 minutes for a single exchange. Not a real-time conversation. Not even a functional back and forth. A single question and a single answer, separated by nearly 3 hours. That is not a communication inconvenience. That is a fundamental severance from every support system, every piece of accessible human knowledge, every doctor and engineer and person who has ever helped you solve a problem in your life. Now consider Cassini, NASA's most accomplished deep space probe, launched in October 1997. No crew, no food requirements, no oxygen, no psychological health to maintain, no return journey needed. Cassini was pure machine, optimized for exactly one purpose: reach Saturn and study it, with every possible advantage, using gravitational slingshots from Venus twice, then Earth, then Jupiter, to build speed across years of carefully calculated trajectory. Cassini still took 6 years and 9 months of continuous flight to reach Saturn's orbit, nearly 7 years, with no passengers, no life support, and no obligation to ever come back. A crewed mission exists in a completely different dimension of complexity. Human beings require food, water, oxygen, medication, radiation shielding, psychological support infrastructure, exercise equipment, and waste processing systems, all of it, every single day for the entire duration. Each of those requirements adds mass. More mass demands more fuel. More fuel adds more mass. The spacecraft, sustaining a crew across 7 years of transit, becomes dramatically heavier than any robotic probe. And heavier means slower. And slower means longer. And longer means the crew needs even more supplies to survive the extended journey. Then there's the return. Cassini never needed to come back? A crew absolutely does. The spacecraft must carry not only the fuel to reach Saturn, but the fuel to break into Saturn's orbit, conduct months or years of operations, break out of Saturn's orbit, and power the multi-year journey home. When aerospace engineers run the full mission architecture: departure from Earth, transit to Saturn, orbital operations, departure from Saturn, transit back to Earth, the estimated total mission duration for a crewed round trip lands somewhere between 14 and 20 years. 14 to 20 years. Translate that into human terms. You board the spacecraft at 30 years old. You leave behind your family, your friends, everything familiar. If absolutely everything goes correctly, no equipment failures, no medical emergencies, no mission-ending disasters of any kind, you return to Earth somewhere between the ages of 44 and 50. You departed as one person. You return as someone your own family will need time to recognize, changed in ways that go far beyond what calendars can measure. Could you do that? Could you spend 7 years just getting there, confined to a living space roughly the size of a standard 2-bedroom apartment? Perhaps 50 square meters total, unable to go outside, unable to change your environment in any fundamental way, unable to leave under any circumstances. 7 years of the same recycled air, the same walls, the same 4 or 5 faces, the same routine, with no exits and no alternatives. That is not rhetorical dramatization. That is the minimum transit time under optimal orbital conditions, using propulsion technology that does not yet exist in operational form. This is, technically, the only vacation in human history that requires purchasing health insurance for 2 consecutive decades. The travel insurance actuaries would have to invent an entirely new risk category. Pre-existing condition clauses would need to account for medical conditions that don't have names yet, because no human being has ever been in deep space long enough to develop them. Time is only the first problem. The second problem will make you realize that even getting off the launch pad is nearly impossible. When you pull into a gas station and fill up your car, the underlying logic is beautifully simple. Fuel goes in the tank. Engine burns the fuel. Car moves forward. As the fuel gets consumed, the car gets lighter, but the car itself, the thing you actually care about, stays the same weight from the moment you leave the driveway to the moment you arrive at your destination. You are never burning part of the car to move the car. Rockets work in a completely different way, and that difference is precisely where every dream of sending humans to Saturn quietly collapses. In 1897, a Russian schoolteacher and mathematician named Konstantin Tsiolkovsky derived an equation that would permanently define the hard ceiling of human ambition in space: the Tsiolkovsky rocket equation. You don't need a single mathematical symbol to understand why it's a trap, just the logic in plain language. A rocket generates thrust by expelling mass out the back. The propellant gets thrown backward at high velocity, and the rocket moves forward in response. Straightforward, but here is where it turns cruel. The propellant itself has mass. To lift that propellant off the ground and accelerate it through space, you need additional propellant. That additional propellant also has mass. So you need more propellant to lift the propellant that lifts the propellant. That third layer of propellant has mass too. The loop never closes. It just keeps cascading downward, each layer demanding a larger foundation beneath it. Not in a straight line, but on an exponential curve that bends upward with increasing aggression the farther and faster you want to travel. The Apollo program makes this concrete in a way that nothing else does. When Saturn V, the most powerful rocket ever successfully launched by human civilization, lifted off from Kennedy Space Center on July 16, 1969, its total weight on the launch pad was approximately 2,900 metric tons, nearly 3,000 metric tons of engineered precision, stacked 36 stories into the Florida sky. What made it to the moon and back a capsule weighing roughly 5 metric tons? 3 men and their return vehicle. The ratio, approximately 95% of Saturn V's entire launch mass, existed purely as propellant and expendable hardware, burned and discarded in stages, just to deliver 5% of its weight to the moon and return it safely. 600 kilograms of fuel and structure consumed for every single kilogram of crew and equipment that completed the journey. And the moon is only 384,000 kilometers away. Saturn, the planet, sits at 1,200,000,000 kilometers, 3,000 times farther. Distance alone doesn't capture why the math becomes catastrophic. What actually governs rocket fuel requirements isn't distance. It's a quantity called delta V, which represents the total change in velocity a spacecraft must execute across every maneuver of its entire mission. Departing Earth's gravity costs delta Vramov, accelerating through deep space costs delta V, breaking into Saturn's orbital vicinity costs enormous delta V. Departing Saturn for the return journey costs delta V again. Breaking back into Earth's vicinity at the end costs delta V one final time. Because of the Tsiolkovsky equation, fuel mass doesn't scale linearly with delta V requirements. It scales exponentially. Each additional unit of required velocity change demands a disproportionately larger mass of propellant to achieve it. And the total delta V budget for a crewed round-trip Saturn mission is not merely larger than the Apollo moon missions, it belongs to a different order of magnitude entirely. Picture it this way. Suppose mission planners determine the crew needs 1 additional metric ton of food, 1,000 kilograms, to survive the extended transit. To actually deliver that 1,000 kilograms to Saturn and back, accounting for the fuel needed to accelerate it, decelerate it, and move it through every mission phase. The rocket may need to carry not 1,000 additional kilograms of propellant, but potentially tens of thousands of additional kilograms, because that extra propellant itself must be accelerated, which demands more propellant, which must be accelerated, which demands more propellant still. Every additional kilogram of cargo creates a cascade of required fuel that ripples all the way back to the launch pad. Engineers call this the tyranny of the rocket equation, and the word tyranny is not chosen casually. There is no elegant workaround, no clever shortcut that makes the physics more forgiving. The equation is what it is, and it does not negotiate. Rough engineering analyses of a crewed Saturn mission architecture, accounting for Earth departure, deep space transit in both directions, Saturn orbital insertion, and operational phases near the planet, suggest propellant requirements that could reach into the tens of thousands of metric tons for the fully fueled launch vehicle. Some frameworks propose that such a mission would require a rocket assembled in multiple pieces across multiple launches, combined in Earth orbit before departure, because no single launch vehicle conceivably buildable could lift the required mass from the ground in one attempt. Saturn V stood 111 meters tall, taller than the Statue of Liberty, standing on its own pedestal, and weighed nearly 3,000 metric tons fully fueled. It was the greatest rocket ever built. It could not get a crew to Saturn. It wouldn't even be in the right conversation. the mission demands something that makes Saturn V look like a proof of concept from a more innocent era of engineering optimism. If reaching the moon required a rocket the size of a 10-story building, filled to roughly 95% capacity with fuel, what does a journey 3,000 times farther demand? Technically, the rocket equation does have a solution. You simply need a launch vehicle considerably larger than the Empire State Building, a propellant budget that approaches the gross domestic product of a small nation, and launch pad infrastructure that doesn't exist anywhere on Earth, completely manageable. But assume someone solves it. Assume the funding materializes, the engineering gets done, the rocket gets built, and the crew launches successfully. The spacecraft clears Earth's atmosphere. The journey is underway. The greatest human expedition in history has begun. And right at that moment, from that very first second beyond Earth's protective magnetic field, the universe begins cooking the crew from the inside. Your SPF 50 sunscreen, the one sitting in your bathroom cabinet right now, blocks roughly 98% of ultraviolet radiation from the sun. You probably consider that impressive. It is, by the standards of Earth-based sun protection. But here's the number that puts it in context. Earth's magnetic field, the invisible electromagnetic shell generated by the planet's spinning iron core blocks, approximately 99.9% of the genuinely lethal radiation streaming through space at all times. The sunscreen handles the mild stuff. The magnetic field handles everything that would actually kill you. Remove the magnetic field, and you are not slightly more exposed. You are standing in a continuous crossfire of high-energy particles with nothing between you and them. Astronauts aboard the International Space Station still orbit within Earth's magnetosphere. They have not escaped its protection. Even so, they absorb radiation at a rate roughly 10 times higher than a person standing on the ground. 10 times. That exposure level is already treated as a serious occupational hazard. NASA enforces strict career lifetime radiation limits for astronauts, and long-duration ISS missions push those limits hard enough that some astronauts are medically restricted from flying again after a single extended stay. The space station sits at roughly 400 kilometers altitude, still cradled inside the magnetic shield, and it's already approaching the boundary of what the human body can tolerate professionally. Beyond the magnetosphere, the calculation changes completely. Deep space between Earth and Saturn is saturated with galactic cosmic rays, GCRs, which are high-energy particles accelerated to near light speed by supernova explosions and other violent events scattered across the galaxy. They arrive from every direction simultaneously, 24 hours a day, 7 days a week, with no pattern and no warning. Unlike the radiation near Earth, which the magnetosphere deflects, GCRs cannot be adequately blocked by any shielding material light enough to carry on a spacecraft. The physics is counterintuitive, but firmly established thick shielding against GCRs actually generates secondary radiation as the particles collide with the shield material, sometimes making the problem worse. There is no material solution that fully protects a crew over a multi-year deep space transit. The radiation reaches them every day for 7 years each way. Then there are solar particle events, what engineers call SPEs, and what the sun produces without reliable warning. When the sun fires a major coronal mass ejection toward a spacecraft, it launches a wave of high-energy protons traveling at a significant fraction of the speed of light. A major X-class solar particle event can deliver a potentially lethal radiation dose in a matter of hours, not days. Hours. Current solar forecasting can provide perhaps 15 to 60 minutes of warning. Before the particle wave arrives, barely enough time to reach whatever storm shelter exists on the spacecraft. Assuming one exists, and assuming it provides meaningful protection over an extended event. In deep space, there is no magnetosphere to deflect the initial wave. There is no Earth-based emergency infrastructure to assist. There is no option to abort to a lower, more protected orbit. The crew sits in the particle stream for however long the event lasts, absorbing whatever dose the event delivers, with no recourse except whatever shielding they managed to bring. Along shielding that had to be weighed against every other gram of the mission's mass budget from the moment of launch. NASA's own radiation risk analyses are unambiguous on this point. A round-trip crewed mission to Mars, which sits far closer to Earth than Saturn, with a total transit time a fraction of what a Saturn mission would require, would expose astronauts to a cumulative radiation dose that exceeds NASA's current career exposure limits for increased cancer risk. The agency has been working for years on how to address this for a Mars mission, and no fully satisfactory solution exists yet. Saturn is not Mars. Saturn is dramatically farther. The transit time is dramatically longer. The cumulative GCR exposure across a 14 to 20-year round trip would dwarf the Mars figures by a factor that makes the Mars radiation problem look manageable by comparison. The long-term consequences of that exposure are not speculative. They are documented in the medical literature with increasing specificity as astronaut health data accumulates. Elevated cancer risk across multiple organ systems, cataracts forming years earlier than they would in non-irradiated individuals, a known effect observed in astronauts who flew even relatively short missions, central nervous system damage, impaired cognition, memory disruption, reduced motor coordination, personality changes, effects observed in animal studies conducted under simulated deep space radiation conditions, with growing concern about their applicability to humans on extended missions. These are not risks that resolve when the mission ends. They are permanent biological changes accumulated over years that the crew carries for the rest of their lives. If you knew with complete certainty, not as a possibility, but as a statistical near inevitability, that spending 7 years in deep space would expose you to continuous ionizing radiation at levels your body was never designed to handle, that somewhere in those years, a solar particle event might deliver a dose that kills you in days, and that whatever you survived would leave your DNA carrying damage that medical science cannot repair mid-mission, would you still get on the spacecraft? The spacesuit, by the way, protects against vacuum and thermal extremes with genuine engineering brilliance. Against deep space radiation, it offers protection roughly comparable to wearing a rain jacket while standing inside an X-ray machine. The materials are simply not the right tool for this particular threat. It would be impressive apparel in almost any other context in the known universe. Radiation attacks from the outside in particles penetrating the hull, penetrating the suit, penetrating the body. It is relentless, and it is invisible, and it accumulates without sensation every second of every day of the transit. But there is something that destroys the crew from the inside, something that requires no external particle source, no solar event, no cosmic phenomenon at all. It begins working on the body from the very first day the spacecraft leaves Earth, using nothing more than the absence of a force the human body has depended on for its entire evolutionary history. Think about the last time you were seriously sick. Flu, injury, whatever kept you flat in bed for 2 weeks. When you finally stood up and walked to the bathroom, your legs felt unreliable. Your arms felt heavier than they should. You felt older, temporarily, in a way that was mildly alarming. 2 weeks of bed rest does that to a body that evolved to move, to carry its own weight, to fight gravity every waking moment. That experience, that brief, recoverable weakness, is a preview. A faint and forgiving preview of what microgravity does to the human body when the exposure isn't 2 weeks, but 7 years. Astronauts returning from 6-month stays aboard the International Space Station, not 7 years, 6 months, show measurable, documented, reproducible physiological deterioration across multiple body systems, muscle mass losses of up to 20% of total skeletal muscle mass over a 6-month mission. Despite mandatory exercise regimens designed specifically to slow that loss, bone density decreases of 1 to 2% per month in load-bearing bones. 1 to 2% every month. To put that in biological context, that is the rate of bone density loss seen in untreated osteoporosis patients in their late 70s. Healthy astronauts in their 30s and 40s are experiencing the skeletal deterioration of elderly individuals, compressed into months rather than decades, because their bones no longer receive the mechanical stress of supporting body weight against gravity. 6 months produces those results. The data is solid, replicated across dozens of astronauts, and it includes post-flight recovery data showing that even with intensive rehabilitation, full recovery of bone density is not always achieved. Some loss persists. After 6 months, model that trajectory across 7 years of transit to Saturn, and the picture that emerges is not merely worse. It enters territory that has no precedent in human medicine, because no human being has ever been in microgravity for 7 years. Bone and muscle modeling studies suggest that losses accumulate in ways that exceed the body's capacity for full regeneration. Even with the most aggressive countermeasures available, the body rebuilds tissue based on the demands placed on it. Remove the demand, remove gravity, and the body interprets the absence of mechanical stress as a signal that the tissue is unnecessary. It dismantles itself with quiet, biological efficiency, month after month. Following instructions written into its physiology long before spaceflight was a concept anyone had considered. The heart is not exempt from this process. The human heart is a pump designed to work against gravity, to push blood upward to the brain, outward to the extremities, to overcome the constant downward pull of Earth's gravitational field. In microgravity, that workload disappears. The heart no longer needs to generate the same pressure to circulate blood effectively. Like any muscle deprived of its training stimulus, it adapts to the reduced demand by becoming smaller and weaker. Cardiac mass decreases. Output efficiency changes. When a crew member who has spent years in microgravity suddenly re-enters Earth's gravity field, the heart that returns is not the same organ that departed. The risk of cardiac complications during re-entry and the immediate post-return period is a documented concern in long-duration spaceflight medicine. Then there is the phenomenon that NASA researchers have named SANS, Spaceflight Associated Neuroocular Syndrome. In microgravity, cerebrospinal fluid redistributes toward the head in ways it never does on Earth, because gravity is no longer pulling it downward. This fluid accumulation creates sustained intracranial pressure that deforms the eyeball, physically reshaping the structure of the eye over time. The result is measurable vision impairment, ranging from mild refractive changes to significant degradation of visual acuity. Approximately 50% of astronauts who have completed long-duration ISS missions show evidence of SANS-related changes. Some of those changes are permanent. A crew member arriving at Saturn after 7 years in microgravity may be seeing the rings through eyes that have been structurally altered by nearly a decade of abnormal fluid pressure. The immune system weakens in microgravity. The mechanisms are still being studied, but the effect is consistent and observed across multiple missions. Latent viruses that the body normally suppresses, including strains of herpes simplex and Epstein-Barr, reactivate in astronauts at significantly higher rates than in matched Earth-based controls, because the immune surveillance that keeps them dormant becomes less effective in the space environment. The gastrointestinal system loses its normal orientation-dependent motility patterns. Sleep architecture degrades, driven by disrupted circadian rhythms in an environment with no natural light cycle and irregular day lengths. The body's systems do not collapse independently. They degrade in parallel, interacting with each other, compounding effects that individually might be manageable, but collectively represent a sustained assault on every major physiological system. After 14 to 20 years of total mission duration, the realistic estimate for a Saturn round trip. What does the returning crew look like? The honest answer is that nobody knows. because no human being has ever experienced anything close to do it. The data ends at roughly 1 year of continuous spaceflight. Beyond that, medicine enters extrapolation territory, and the extrapolations are not encouraging. The models suggest bodies that have aged physiologically at rates that bear little relationship to chronological age, skeletons that resemble those of people in their late 80s or 90s, cardiovascular systems operating at margins that make re-entry, landing, and the physical demands of returning to a gravity environment genuinely life-threatening. The exercise protocol on the International Space Station requires crew members to exercise for 2 hours every single day. 2 hours of mandatory physical activity, carefully designed by exercise physiologists, tracked and monitored just to slow the rate at which the body destroys itself, not to stop it, not to prevent the losses, to slow them. 2 hours a day of hard work, and the body still loses muscle, still loses bone, still undergoes cardiac remodeling, still develops SANs. The exercise is not a solution. It is a delay tactic against a process the human body runs automatically and relentlessly the moment gravity is removed. If you knew, with complete certainty, that the journey would return you to Earth with the skeleton of a 90-year-old bones, fragile enough to fracture under loads your pre-mission body handled without thought, would you still want to go? The body collapses from within, and when that happens, across 7 years of absolute isolation, with no escape, no relief, and no one to call, the mind does not wait patiently for the body to finish. It starts breaking down at exactly the same time. Think about the loneliest you have ever felt. Maybe you lost your phone for a day and felt that strange low-grade anxiety of being unreachable, untethered from everyone you know. Maybe a blizzard kept you housebound for a week, cut off from the world outside, and by day 4, the walls started feeling closer than they actually were. That feeling, that mild, temporary, entirely survivable discomfort, is the faintest possible echo of what 7 years of absolute isolation in deep space does to a human mind. Not 7 days, not 7 weeks, 7 years, in a metal container, with no exit, no possibility of stepping outside, no change of scenery that isn't a screensaver, no strangers to encounter, no unexpected conversations, no spontaneous anything. The same 4 or 5 people, every meal, every morning, every crisis, every silence, for 7 years straight, and nowhere to go when it becomes unbearable. Because there is nowhere to go, the communication delay alone would restructure the psychology of daily existence in ways that are difficult to fully imagine from the comfort of a planet with functioning cell towers. A radio signal traveling at the speed of light takes between 68 and 83 minutes to reach Saturn from Earth, depending on where the 2 planets sit in their respective orbits. One way? So a message sent from the spacecraft arrives at mission control somewhere between 68 and 83 minutes after transmission. Mission control reads it, formulates a response, transmits back. That return signal takes another 68 to 83 minutes to arrive at the spacecraft. Total round-trip time for a single exchange between 2 hours 16 minutes and 2 hours 46 minutes, minimum, under the most favorable orbital geometry. No real-time communication of any kind. No phone calls. No video conversations where you can see someone's face react to what you just said. No calling your mother when the anxiety becomes overwhelming at 2 in the morning. You compose a message into the void, and then you wait for hours to receive anything back. And whatever comes back is already outdated by the time it arrives. A response to a version of your situation that existed nearly 3 hours ago, from people who cannot actually see what is happening to you right now. That is not a minor inconvenience. That is the permanent psychological texture of the entire mission. The research on extreme isolation gives a clear picture of what happens to human minds under far less demanding conditions than a 7-year deep space transit. The HICs studies NASA-funded simulations conducted in a habitat on the slopes of Mauna Loa in Hawaii, where small crews lived in isolation for periods of up to 1 year, documented measurable increases in anxiety, interpersonal conflict, communication breakdown, and psychological stress responses within months in participants who knew they could leave if necessary, who were on the same planet as everyone they loved, and whose isolation lasted a fraction of what a Saturn mission would require. The Mars 500 study, conducted in Moscow between 2010 and 2011, had 6 crew members simulate a 520-day Mars mission in complete isolation. By the end, the crew showed significant evidence of physical inactivity, sleep disruption, and psychological withdrawal. One participant spent 40% of his waking hours asleep, a recognized response to depression and hopelessness. 520 days, less than 18 months, in a facility in Moscow. Antarctic winter overstations, where small crews spend roughly 8 to 9 months in genuine geographic isolation. During the polar winter, consistently document a syndrome researchers call the third quarter phenomenon, a predictable deterioration in mood, motivation, cognitive performance, and group cohesion that sets in roughly halfway through the isolation period, when the end still feels impossibly distant. Crews develop what psychologists term behavioral sink: increased irritability, withdrawal, cognitive rigidity, loss of emotional regulation in an environment where everyone at least shares the same planet and the same gravitational field as the rest of humanity. 7 years falls so far outside any data set that psychologists who study extreme isolation use a specific term for it: terra incognita, unknown territory. There is no research. There are no case studies. There is no longitudinal data on what the human mind does when confined in a small space, separated from all of civilization by a communication delay measured in hours, for 7 consecutive years. The honest scientific's position is that nobody knows, and the extrapolations from shorter studies are not optimistic. The danger's not only individual psychological deterioration, though that alone would be mission-threatening. The danger compounds inside the group, a crew of 4 or 5 people, locked together in 50 square meters for years, under conditions of physiological stress, sleep disruption, radiation exposure, and chronic uncertainty, will generate interpersonal friction. That is not a prediction. It is a documented certainty from every isolation study ever conducted. Conflict emerges, alliances form and fracture. Grievances accumulate in an environment where there is no physical space to create distance from the person who is irritating you, no outside relationships to provide perspective, no way to decompress that doesn't involve the same people you are decompressing from. In deep space, interpersonal conflict inside the crew is not merely uncomfortable, it is operationally lethal. A crew member in a psychological crisis making a decision about a navigation burn, a system repair, a medical emergency, a single judgment call made from inside a deteriorating mental state can end the mission and kill everyone aboard. There is no crew psychologist flying along. There is no intervention possible from Earth in real time. There is no emergency evacuation of a crew member who is no longer mentally fit to participate in mission-critical operations. Whatever happens inside that spacecraft, the crew handles alone, with the tools they brought and the mental resources they have left. NASA has formally acknowledged this. In published assessments of risks associated with long-duration deep space exploration, the agency identifies human behavioral health and performance, the psychological dimension of extended missions, as one of the most significant unresolved challenges standing between current capabilities and genuine deep space human exploration. Not one of several engineering problems with clear solution pathways, an unresolved challenge. The phrasing is careful and institutional, but the meaning is direct. We do not yet know how to keep human minds functional and operationally reliable across the duration a Saturn mission would require. Have you ever sent a text to someone and then sat there watching the screen, waiting for the three dots to appear, feeling that low-level tension of unanswered communication? Now imagine you send that message at 8 in the morning. You receive the reply at 11. Not because the other person was busy or distracted, but because physics itself imposes a minimum 2-hour 46-minute delay on every single exchange. And that is the permanent, unchangeable communication reality of your entire mission, every day, for 7 years. The patience required for this mission has a specific shape. You send a message that says, "Are you okay?" at 8 in the morning, and you receive the word "fine" at 11, and you do that, in some variation, every single day for 7 years, knowing that the people responding to you are seeing a version of your situation that is almost 3 hours out of date, and that if something is genuinely wrong at this moment, they cannot help you in time regardless. You have survived the distance. You have survived the mathematics of fuel that almost prevented departure. You have survived years of invisible radiation cooking you from the outside. You have survived a body that dismantled itself in the absence of gravity. You have survived the slow erosion of a mind pushed past every boundary isolation research has ever studied. You made it to Saturn, after everything you actually made it. And this is where things get genuinely worse. When someone says, "land on a planet," a specific image forms automatically in the mind. The spacecraft descends. The landing gear deploys. Dust kicks up beneath the thrusters. The crew walks down a ramp and plants their boots on solid ground. It's the image from every space film ever made, every artist's rendering of planetary exploration, every childhood imagination of what reaching another world looks like. Saturn does not have ground. Not thin ground. Not soft ground. Not ground covered in liquid or ice that might be carefully navigated. No ground at all. Saturn is a gas giant. A world composed of approximately 96% hydrogen and helium, with the remaining fraction split between methane, ammonia, and trace compounds. There is no solid surface anywhere within the planet. No crust, no bedrock, no defined boundary where atmosphere ends and something firmer begins. The planet is, from its outermost cloud layers all the way to whatever exists at its mathematical center, a sphere of increasingly compressed gas and fluid that transitions gradually into states of matter that don't have clean, everyday names. This eliminates the entire conceptual framework of landing as a meaningful mission objective. There is no point to aim for, no coordinates to designate as a touchdown zone, no place to anchor a habitat, no surface to drive a rover across, no ground to sample with a drill. The thing most people picture when they imagine a crewed Saturn mission, the dramatic moment of arrival, boots on an alien world, cannot happen, because the alien world in question has no surface on which boots could stand. The atmosphere is not simply a layer to pass through on the way to something solid. It is the entirety of what Saturn is, extending downward for tens of thousands of kilometers, growing denser and more hostile with every kilometer of descent. Near the visible cloud tops, atmospheric pressure is roughly 1 atmosphere familiar, comparable to standing at sea level on Earth. Descend further, and pressure climbs with brutal consistency. At deeper levels, the hydrogen gas transitions into liquid hydrogen under conditions no material science on Earth can replicate. Deeper still, that liquid hydrogen is thought to transition into metallic hydrogen, a phase in which hydrogen atoms are so compressed that electrons move freely between them, giving the substance properties of a liquid metal. This state exists nowhere on Earth and has only been created briefly in laboratory conditions using extreme compression. At the core of Saturn, current scientific estimates place the temperature at approximately 11,700 degrees Celsius. The surface of the Sun, the visible outer layer that sustains all life on Earth, reaches approximately 5,500 degrees Celsius. Saturn's core runs more than twice as hot as the surface of the Sun. In September 2017, NASA deliberately directed Cassini into Saturn's atmosphere. The reasoning was planetary protection, preventing the probe from potentially contaminating Enceladus or Titan after decades in space. Engineers calculated a final plunge trajectory, and Cassini entered the upper atmosphere. The spacecraft lasted minutes. Increasing atmospheric density first destabilized its orientation, then aerodynamic forces overwhelmed its structure. And Cassini, a machine costing $3.26 billion, representing the combined engineering of 17 nations, was completely melted and vaporized. Not crashed, not broken. Dissolved into a planet that does not permit solid objects to persist inside it. So if landing on Saturn is physically impossible, what does a crewed Saturn mission actually mean? It means landing on one of Saturn's moons. The planet has 82 confirmed moons, ranging from small irregular bodies to world-sized objects with their own geological complexity. The most likely target would be Titan, the largest moon, the only moon in the solar system with a dense atmosphere and the most scientifically compelling destination in the Saturn system. If not Titan, perhaps Enceladus, the small ice-covered moon, whose subsurface ocean vents plumes of water vapor and organic compounds into space, making it one of the most important astrobiological targets ever identified. Both destinations are nightmares of a completely different kind, which this story reaches shortly. But if there is no ground to land on, where exactly does a crew land? The honest answer on a moon that presents its own entirely separate set of conditions capable of killing everyone aboard in ways Saturn's atmosphere never even gets the chance to attempt. The landing procedure for Saturn itself is, technically, extremely simple. You fly in, the spacecraft dissolves. No landing gear required, no touchdown calculations, no post-landing checklist. The planet handles everything automatically and permanently. Zero post-mission complexity, no ground. But to get to that no-ground place, you first have to fly through the most beautiful and most dangerous thing in the entire solar system. Saturn's rings are the first thing anyone thinks of when the planet comes to mind. That iconic image, the pale golden sphere wrapped in those perfect luminous bands, has been reproduced on classroom walls, observatory posters, and textbook covers for generations. From a distance, they look like something designed with intention. Delicate, geometric, serene. That image is accurate from far away. From inside the rings, the reality is categorically different. Saturn's ring system stretches roughly 282,000 kilometers from its innermost edge to its outermost boundary, a span wider than the distance from Earth to the Moon. Across that expanse, the rings contain an estimated several hundred trillion individual particles, ranging from fine dust measured in micrometers to boulders the size of houses, with every scale of debris distributed between those extremes, predominantly water ice mixed with rocky material. They are not a static organized structure. They are a dynamic, constantly shifting environment of particles in orbital motion, driven by gravitational resonances from Saturn's dozens of moons, the planet's own gravity, and electromagnetic forces from Saturn's powerful magnetic field. The problem for a spacecraft is not what the rings look like. It's what they do to anything traveling through them at orbital velocity. A spacecraft approaching Saturn arrives at a velocity measured in tens of kilometers per second relative to the planet. This is not a choice. It is the consequence of orbital mechanics and gravitational dynamics. At 30 kilometers per second, a particle of ice the size of a grain of sand carries kinetic energy equivalent to a rifle bullet. Not roughly equivalent, mathematically equivalent, based on the relationship between mass, velocity, and kinetic energy. A grain of sand at that speed punches through spacecraft materials the way a high-caliber round punches through sheet metal. The rings contain not grains of sand, but hundreds of trillions of particles across a size range extending from micron-scale dust to objects massing as much as a small building. The probability of impact during ring transit is a direct function of the cross-sectional area of the spacecraft, the particle density along the chosen trajectory, and the duration of the transit. Cassini navigated this environment with genuine engineering ingenuity. Mission planners identified the Cassini division, a relatively sparse gap in the ring system, roughly 4,800 kilometers wide, as a safer transit corridor. During its final ring-grazing passes, engineers oriented the spacecraft so that its large high-gain antenna faced the direction of travel, using the dish as a physical shield against ring particle impacts. The antenna was not designed for that purpose. It was repurposed as armor because no better option existed. A crewed spacecraft presents a fundamentally harder problem. The life support systems, habitat modules, fuel tanks, and structural components required to keep human beings alive across a multi-year mission make the vehicle dramatically larger than Cassini. Cross-sectional area increases accordingly. A larger cross-section means higher probability of impact during ring transit, with no proportional increase in the vehicle's ability to survive those impacts. The hull protecting the crew from vacuum and thermal extremes was not engineered to absorb hypervelocity particle strikes. A sufficiently large ring particle hitting the hull at 30 kilometers per second does not produce a dent. It produces a hole and holes in spacecraft hulls in deep space, with no rescue available for 7 years in any direction, are not engineering problems with solutions. They are cause of death entries in an accident report written years after the fact by people who were never there. The gravitational complexity compounds everything. Saturn's major moons, Titan, Enceladus, Mimas, Rhea, Dione, Tethys, each exert gravitational influence on any spacecraft operating in the Saturn system. These influences interact and overlap and shift continuously as the moons move through their orbits. A navigation solution accurate at one moment becomes inaccurate minutes later as the gravitational landscape changes. Maintaining a stable trajectory through the ring system requires continuous calculation and correction, using onboard computers that have spent years absorbing radiation damage, operated by a crew running on degraded cognitive capacity after years in deep space. The margin for navigational error is narrow. Drifting into a denser ring region, missing a correction burn by seconds, the consequences are permanent, and nobody is coming to help sort them out. Would you drive at 30,000 kilometers per hour through a minefield in a vehicle never designed to absorb impacts, with no mechanic reachable if something fails, no hospital within years of travel, and no route home if the vehicle takes damage that stops it cold? The view would be extraordinary, genuinely the most visually spectacular drive in the solar system. 5 stars, no question, breathtaking from every angle. The survival rate among crews who have attempted it and returned to post a review, however, remains unconfirmed. You cleared the rings. The ship is still in one piece, but now comes the problem. Nobody really talks about how do you stop. When you drive a car and need to slow down, you press the brake pedal. The brake pads clamp against the rotors. Friction converts kinetic energy into heat, and the car decelerates. Simple, immediate, reliable. You have probably done it 10,000 times without thinking about the physics involved. In space, that option does not exist. There is no friction, no road to push against, no medium of any kind that resists motion. In the vacuum between planets, an object in motion stays in motion indefinitely, at the same speed, in the same direction, until something actively changes that. Newton's first law, operating without exception, forever. To slow down in space, you burn fuel. Specifically, you point your engines in the direction of travel and ignite them, pushing thrust against your own momentum until enough velocity bleeds off to achieve whatever speed the mission requires. The fuel does not supplement your motion, it fights it. You are spending propellant to undo the very velocity you spent propellant to build up in the first place. Every meter per second you gained on the way out must be paid for again on the way in. A spacecraft arriving at Saturn does so at an enormous velocity, relative to the planet approximately 30 kilometers per second, depending on the specific trajectory flown. At that speed, if the engines do not fire at precisely the right moment, for precisely the right duration, the spacecraft does not slow down. It does not enter orbit. It flies past Saturn, continuing outward into the deeper solar system, carrying its crew into a trajectory from which no return is possible with any fuel remaining aboard. 7 years of travel, arriving at the destination and missing it completely, not because of navigation error, but because the engines failed to perform a single critical burn at the single moment it was required. This burn has a name, the orbital insertion burn, often called the capture burn. It is the maneuver that transforms a flyby trajectory into a captured orbit, and it is one of the most consequential single events in any deep space mission. Everything before it, the launch, the years of transit, the radiation exposure, the physiological deterioration, the ring passage, all of it is prologue. The capture burn is the moment that determines whether the mission exists at all. Cassini's Saturn orbit insertion burn on July 1st, 2004, lasted 96 minutes, 96 continuous minutes of engine firing, consuming enormous quantities of propellant to scrub enough velocity off the spacecraft to allow Saturn's gravity to capture it into orbit. That was for Cassini, an uncrewed probe carrying no life support, no return fuel, no habitat, no crew provisions. Cassini arrived lean, stripped to its scientific instruments and its fuel, with no obligation to ever come home, and it still needed 96 minutes of continuous engine burn just to stop. A crewed spacecraft cannot arrive lean. It carries everything needed to keep human beings alive across the entire mission duration, and critically, it must carry the fuel required to leave Saturn's orbit when operations are complete and begin the multi-year journey home. That return fuel must be present at Saturn before the capture burn begins, because there is no way to acquire it afterward, which means the spacecraft that executes the capture burn is dramatically heavier than Cassini was. A heavier spacecraft requires a longer burn, consuming more fuel. To achieve the same orbital capture, more fuel burned during capture means less fuel available for the return trip, which means the mission must carry even more fuel at departure to ensure enough remains after capture for the journey home. The rocket equation from Part 2 does not stay in Part 2. It follows the mission all the way to Saturn and sits there waiting, still compounding, still demanding more mass for every additional gram of payload. This is, in part, why Cassini never came home. It was not purely a choice. NASA's engineers ran the calculations and determined that a version of Cassini capable of returning to Earth would have required so much additional propellant to execute the capture burn with the added mass, to then escape Saturn's gravity well, to then conduct a multi-year return transit that the mission as conceived and funded could not have supported it. The science return per dollar would have collapsed under the weight of the fuel requirements, so Cassini stayed. It orbited Saturn for 13 years, transmitted everything it could, and then went into the atmosphere. It never had the fuel to leave. Now place a crew in that same arithmetic. 7 years of travel to reach this moment. The crew is at Saturn. The capture burn window is open a specific period lasting minutes, during which the engines must fire if orbital insertion is to succeed. The burn begins, and then, somewhere in those 96 minutes of continuous engine operation, something fails. A turbopump cavitates, a valve sticks, a fuel line develops a leak under the thermal stress of prolonged firing. The engine shuts down early, or never reaches full thrust, or cuts out entirely. The spacecraft has not shed enough velocity. Saturn's gravity is insufficient to capture it. The trajectory carries the crew onward, past the planet, into the outer solar system. You spent 7 years flying to this exact point. The engines fired, and then they didn't. What do you do? There is no answer to that question that does not end with the crew dying somewhere beyond Saturn, in a spacecraft that has run out of options along with its fuel. This is not a scenario that engineering redundancy eliminates. It reduces the probability. But probability is not certainty, and certainty is the only acceptable standard when the failure mode is irreversible death in deep space with no rescue possible. This is also, incidentally, the only moment in recorded history where the phrase, "let's just see what happens," functions as the single worst possible response to a situation. The result of seeing what happens is already fully determined by orbital mechanics, and it is not encouraging. You made it into orbit. The burn held. The crew is captured around Saturn, alive, exactly where the mission plan required them to be. Now, they need fuel to get home, and someone in the mission architecture meeting, at some point, raised a hand and said, "Why not just make the fuel there?" It sounds elegant. It sounds like the kind of creative problem solving that defines great engineering. It sounds that way right up until you understand what it actually means. Every road trip in America runs on the same quiet assumption somewhere along the route. There will be a gas station. You do not carry all the fuel for the entire journey at departure. You carry enough to reach the next stop, refuel, and continue. The infrastructure exists. It has always existed for your entire driving life, and you have never needed to think seriously about what happens if it doesn't. ISRU in situ. Resource utilization is the space exploration equivalent of that assumption, applied to a place where no infrastructure exists, no supply chain has ever reached, and no human being has ever set foot. The concept is straightforward in principle. Instead of carrying all return fuel from Earth, manufacture it on-site using local resources. In the Saturn system, the primary candidate for that local resource is Titan. Titan's surface is covered with lakes, rivers, and seas of liquid hydrocarbons, predominantly methane and ethane. The Cassini mission confirmed this beyond any scientific doubt. Titan has more liquid hydrocarbon on its surface than all of Earth's known oil and gas reserves combined. From a pure resource perspective, the raw material for fuel production exists there in extraordinary abundance. On paper, the idea of mining Titan's hydrocarbon lakes to produce propellant for a return journey is not scientifically absurd. The chemistry is understood. The energy potential is real. The gap between understood in principle and executable in practice, with human lives depending on the outcome, is where the idea comes apart entirely. To extract liquid methane from Titan's surface and process it into usable rocket propellant, the mission would need pumping systems to collect the raw hydrocarbon, filtration and separation equipment to isolate usable compounds from the complex chemical mixture present in Titan's lakes. Chemical processing reactors to convert those compounds into propellant suitable for the spacecraft's engines, storage systems to hold the processed fuel safely under cryogenic conditions, and transfer systems to load that fuel into the spacecraft's tanks. Every single one of these systems must function reliably, continuously, and without failure in an environment where the surface temperature sits at negative 179 degrees Celsius, colder than the boiling point of nitrogen, cold enough to liquefy gases that behave normally on Earth. Every seal, every pump, every valve, every electronic controller in that entire processing chain must operate at temperatures that make standard engineering materials brittle, that cause lubricants to solidify, that push thermal management systems to their absolute limits. And every component of that system arrives at Titan after 7 years of continuous exposure to deep space radiation. The same radiation that has been degrading the spacecraft's electronics, weakening its structural materials, and altering the properties of every polymer and composite in the vehicle since the day it left Earth orbit. The components were designed and tested in Earth conditions. they have never operated in anything resembling Titan's environment. The combination of extreme cold, toxic atmospheric chemistry, and 7 years of radiation damage creates operating conditions for which no engineering precedent exists. No ISRU technology has ever been tested in conditions remotely comparable to Titan's surface, not in a simulation, not in analog environments. The hardware concepts exist in research papers and preliminary design studies. NASA and ESA have both acknowledged, in formal assessments of outer solar system exploration, that ISRU at Saturn is theoretically feasible, but that no viable technical roadmap for practical implementation currently exists. That is careful institutional language for, we do not know how to actually do this yet, and we certainly have not built anything that has been proven to work. Now consider what a single component failure means in this context. The processing reactor develops a crack under thermal stress. The pump motor seizes because a lubricant failed at -179 degrees Celsius. A filtration membrane clogs with a compound that Titan's chemistry produces in ways the designers did not fully anticipate. Any one of these failures halts fuel production. A halted fuel production means no return propellant. No return propellant means the spacecraft cannot leave Saturn's orbit. A spacecraft that cannot leave Saturn's orbit with a crew aboard, 7 years from Earth, with no resupply or rescue mission possible within any time frame compatible with human survival, has only one outcome. The timing pressure intensifies everything. Orbital mechanics dictates that the alignment between Saturn and Earth that enables an efficient return trajectory does not remain open indefinitely. These launch windows, the periods during which a departure burn from Saturn orbit, can place the spacecraft on a trajectory that reaches Earth with manageable fuel expenditure, occur on schedules determined by planetary orbital periods. Miss the window, and the crew must wait, not weeks, potentially 1 to 2 years for the next viable alignment, 1 to 2 years of additional time in the Saturn system, consuming supplies that were calculated for a specific mission duration, waiting for a fuel production system that may or may not be repaired. In a spacecraft that is aging every day, it stays in orbit. Would you stake your life and the lives of everyone on the mission on a machine that has never been tested in the environment where it must work? Assembled from components degraded by 7 years of radiation, operating at temperatures that push every material to its limits, with a failure rate that only needs to reach 100% once to make the entire mission unrecoverable. The ISRU concept for a Saturn mission is essentially this. You are dropped into the middle of the Sahara Desert with a set of well-drawn blueprints for a water well, a toolkit that arrived in flat-pack boxes, and a friendly send-off of, figure it out. Good luck. The theory is sound. The execution depends on conditions nobody has tested, hardware nobody has validated, and a margin for error that is exactly 0. The fuel problem is unsolved. The clock is running. And while the crew wrestles with machinery that may or may not produce enough propellant to get them home, Saturn itself has been quietly doing something to the spacecraft that no amount of fuel can fix, bombarding it with radiation so intense that it makes the deep space transit look like a mild inconvenience. You already know that Earth's magnetic field protects you. That invisible electromagnetic shield, generated by the churning molten iron in Earth's core, deflects the constant stream of charged particles pouring out of the sun and deflects the high-energy cosmic rays arriving from across the galaxy. Without it, the surface of Earth would be bathed in radiation levels incompatible with complex life. The field is not a luxury. It is the reason biology as we know it exists on this planet at all. Saturn also has a magnetic field. A powerful one, roughly 500 times stronger than Earth's in terms of magnetic moment. And here is where the similarity ends, because Saturn's magnetic field does not primarily protect things inside it. It traps them. The mechanism works like this. Charged particles, high-energy electrons and protons from the solar wind, from cosmic rays, from Saturn's own ionosphere, and from the plasma ejected by Saturn's volcanic moon, Enceladus get captured by the magnetic field lines and cannot escape. Instead of being deflected away, they become locked into the field, spiraling back and forth along magnetic lines between the planet's north and south poles, bouncing endlessly, accelerating as they go. Over time, these particles accumulate into intense belts of trapped radiation surrounding the planet, the same basic phenomenon as Earth's Van Allen belts, but operating at a scale and intensity that makes Earth's version look manageable by comparison. Earth's Van Allen belts are genuinely dangerous. Spacecraft transiting them on the way to the moon during Apollo moved through quickly. Minimizing exposure time, satellites in certain orbital bands require radiation-hardened electronics to survive the belt environment. The belts have destroyed or damaged spacecraft that lingered within them too long. And yet, by the standards of what surrounds Saturn, Earth's radiation belts are a minor inconvenience. Saturn's radiation belts are stronger, broader, and more persistent than Earth's. The inner belt, concentrated closest to the planet, contains trapped protons and electrons at energy levels that exceed what Earth's belts produce. The outer belt extends across a vast region of space surrounding the planet, creating an environment where the baseline radiation flux, the amount of ionizing radiation passing through any given point per unit of time, would be lethal to an unprotected human in a matter of days, not years, not months, days. The effect on electronics is relentless and cumulative. High-energy particles passing through semiconductor materials displace atoms from their crystal lattice structures, gradually degrading the material's electrical properties in a process called displacement damage. They deposit charge in insulating layers of microchips, causing transistors to switch states unexpectedly, corrupting memory, generating false sensor readings, and triggering spurious commands, a phenomenon called single event effects that has caused real operational problems on real spacecraft. Solar cells darken and lose efficiency as their semiconductor junctions accumulate radiation damage, reducing power generation precisely when the mission depends on every watt available. Sensors drift out of calibration. Navigation instruments produce readings that no longer accurately reflect reality. Cassini was engineered specifically to survive the Saturn radiation environment. Its electronics were radiation hardened. Its design incorporated shielding around the most sensitive components. Mission planners carefully selected orbital trajectories to minimize time spent in the most intense radiation zones. NASA's engineers spent years optimizing the spacecraft's architecture against the known radiation environment before a single component was manufactured. And even with all of that preparation, Cassini accumulated measurable radiation damage over the course of its 13-year mission. The spacecraft's systems degraded. Certain instruments experienced anomalies traceable to radiation effects. The engineering team managed these effects carefully, working around limitations that accumulated year by year. A crewed spacecraft is not Cassini. It cannot be optimized purely for radiation survivability because it must simultaneously support human life, carry return propellant, maintain atmospheric pressure, regulate temperature across inhabited volumes, and perform dozens of other functions that each impose their own mass and design constraints. The radiation shielding that would adequately protect the crew and the spacecraft's critical electronics in Saturn's radiation belt environment would need to be substantially measured, not in kilograms, but in metric tons of dense shielding material surrounding the crew habitat and the most critical systems: lead, polyethylene, water. The most effective shielding materials are heavy, extremely heavy, and every additional ton of shielding mass carried to Saturn is subject to the full tyranny of the rocket equation, multiplying the required propellant at departure by a factor that compounds all the way back to the launch pad. The crew inside that habitat, even with substantial shielding, would not be fully protected. Shielding attenuates radiation. It reduces the dose, but it cannot eliminate it entirely, particularly against the highest energy particles that Saturn's belts contain. The crew would be absorbing radiation continuously throughout their time in Saturn orbit, on top of the 7 years of deep space transit radiation they already accumulated on the way there. The total cumulative dose over the full mission transit out, Saturn orbital operations, transit home would reach levels that current radiation medicine has no precedent for managing in a living human being. There is a geographic reality that makes this unavoidable. Every operationally useful orbit around Saturn, every trajectory that puts the spacecraft in a position to conduct meaningful science, to approach the moons of interest, to execute the maneuvers required for the mission passes through regions of significant radiation intensity. There is no clean orbit that keeps the spacecraft comfortably outside the radiation environment, while still allowing the mission to function. The moons worth visiting sit within the radiation belt structure. The approaches to Titan, to Enceladus, to any scientifically relevant destination in the Saturn system pass through zones of elevated particle flux. You cannot do the mission and avoid the radiation. The geometry does not permit it. You traveled 7 years to reach this place. You survived the transit radiation, the microgravity deterioration, the psychological erosion, the ring passage, the capture burn. You are in orbit around Saturn, one of the most extraordinary achievements in the history of human exploration. And you are standing, in every meaningful physical sense, inside a microwave oven the size of a small planet, one that operates continuously, that you cannot switch off, that you cannot step outside of, and that is simultaneously degrading your body and eating through the electronics that keep your spacecraft functional and your life support operational. Saturn is, when you consider the complete picture, the only planet in the solar system with a fully automated defense system already in place. No weapons required, no targeting necessary. It simply generates a radiation environment so intense that anything biological or electronic that spends meaningful time within it accumulates damage that cannot be repaired, only managed until management is no longer sufficient. The system works with remarkable consistency. It has been working for billions of years without interruption, and it will continue working long after any spacecraft humanity might send has been reduced to a drifting collection of radiation-damaged components. You made it through the radiation belts. You are still alive. The spacecraft is still functioning within acceptable parameters, and Titan hangs in the viewport, the largest moon, the most complex moon, the one with an atmosphere and liquid on its surface, and the best chance of providing somewhere to actually stand. The most beautiful destination in the Saturn system. The one place that looks, from a distance, almost welcoming. Titan has its own secrets, and none of them are welcoming. Titan sounds like paradise. That is not poetic exaggeration. It is the genuine first impression the moon produces when you examine its basic characteristics against the checklist of what makes a world habitable. Dense atmosphere check. Atmospheric pressure at the surface roughly 1.5 times Earth's sea level pressure. Well within the range a human body can tolerate structurally. Weather systems check. Clouds, rain, rivers, lakes, and seas. An active hydrological cycle operating on a world-size scale. Stable surface check. Solid ground to stand on. Varied terrain, dunes, plains, mountainous regions made of water ice. By the surface level description alone, Titan reads like the most Earth-adjacent environment in the entire solar system. Beyond Earth itself, every single one of those reassuring characteristics conceals something that kills you. The temperature at Titan's surface is -179 degrees Celsius. Not cold in the way that Antarctica is cold, or in the way that the upper atmosphere is cold, or in the way that any environment a human being has ever survived unaided is cold. -179 degrees Celsius is colder than the boiling point of liquid nitrogen. the substance that laboratories use to freeze biological samples into long-term preservation. At -179 degrees, nitrogen, which makes up about 78% of Earth's atmosphere and which you are breathing right now without giving it a second thought, is a liquid. The baseline temperature of Titan's surface is cold enough to liquefy the air of Earth. Exposed human tissue at that temperature does not freeze slowly. It undergoes cryogenic destruction in seconds, cells rupturing as their water content freezes and expands. Biological structures collapsing in ways that no medical intervention can reverse. The rain that falls on Titan is not water. It is liquid methane, the same compound that, on Earth, is the primary component of natural gas, the fuel burned in kitchen stoves and industrial furnaces. Methane on Titan exists at a temperature where it behaves as a liquid, falling from clouds of methane and ethane vapor, pooling on the surface, flowing in rivers carved through the terrain over geological timescales. The Cassini mission mapped these features in detailed drainage networks, alluvial fans, vast seas in the polar regions, Ligaea Mare, one of the largest methane seas in Titan's northern hemisphere, covers an area comparable to the combined surface area of Lake Huron and Lake Michigan. These are not small features. They are world-scale liquid bodies, and they are composed entirely of hydrocarbons that are acutely toxic to Earth biology. The rivers and lakes follow the same pattern. What looks, from orbital imagery, remarkably like the river systems and lake districts of Earth is in reality a landscape saturated with liquid methane and ethane being a slightly heavier hydrocarbon cousin of methane, also a component of natural gas on Earth, also toxic to living tissue, also present in quantities that make Titan's surface the largest known reservoir of liquid hydrocarbons in the solar system. More liquid hydrocarbon exists on Titan's surface than in all of Earth's proven oil and gas reserves combined. It is an ocean of fuel on a world where the temperature means it stays liquid permanently, and where none of it is safe to touch, drink, or exist near without total physical isolation from it. The atmosphere completing this picture is 98% nitrogen, which sounds superficially similar to Earth's nitrogen-rich air until you add what comes with it. Titan's atmosphere is thick with complex organic molecules, called tholins, reddish-brown photochemical smog produced when nitrogen and methane in the upper atmosphere are broken apart by ultraviolet radiation from the sun and reassemble into increasingly complex organic compounds that drift downward and coat everything on the surface. Tholins are not simply unpleasant. They are chemically reactive organic compounds that would cause chemical burns on contact with skin and eyes. The haze they create is so thick and so uniform that Cassini's cameras, during the Huygens probe's descent through Titan's atmosphere in January 2005, captured an orange-brown murk that obscured any view of the surface until the probe had descended well below the main haze layers. Breathing this atmosphere without a sealed suit would mean inhaling a mixture of nitrogen, methane, and complex toxic organics. The outcome is not ambiguous. The spacesuit required to keep a human being alive on Titan's surface would need to satisfy a set of simultaneous requirements that push current materials, science, and engineering to their limits. It must maintain internal temperature warm enough for human survival against an external environment at -179 degrees Celsius, a thermal gradient of roughly 215 degrees across the suit's insulating layers. It must be completely sealed against an atmosphere that contains chemically reactive compounds capable of degrading many standard materials over time. It must withstand the surface pressure of 1.5 atmospheres without leaking or structurally compromising. It must allow sufficient mobility for a crew member to conduct meaningful surface operations, and it must do all of this reliably, continuously, for the duration of surface operations, knowing that any breach, any crack in a visor, any seal failure in a glove joint, any puncture from a sharp surface feature immediately exposes the wearer to an environment that will kill them before any assistance can be rendered. NASA's Dragonfly mission is the agency's answer to the question of how to explore Titan. Dragonfly is a rotorcraft lander, a drone-like vehicle designed to fly through Titan's dense atmosphere, land at multiple sites, collect samples, and conduct scientific analysis. It is uncrewed, entirely robotic, designed by some of the most capable aerospace engineers on the planet, specifically for Titan's conditions, with no requirement to keep humans alive, no life support systems, no return journey. Dragonfly is expected to arrive at Titan in 2034, nearly a decade from now. After years of development and refinement, NASA is sending a robot because sending a person to the same environment is not something the agency considers operationally feasible under any current planning framework. If you had to wear a fully sealed protective suit every moment of every day, never removing it, never breathing unfiltered air, never feeling a surface with ungloved hands for the entire duration of your time on another world, what would you call that experience living, or simply not dying? At considerable inconvenience and under constant threat, Titan is, at its core, Earth if someone replaced every molecule of water with hydrocarbon fuel, set the thermostat to -179 degrees Celsius, and filled the sky with toxic orange smog. The Earth-like features are real. The habitability they imply is entirely an illusion produced by viewing the moon from a comfortable distance. The environment can kill you in a dozen different ways simultaneously. The equipment required to survive it is operating at the edge of what engineering can produce. And when something goes wrong, when the suit fails, when the equipment breaks, when the medical emergency happens, there is a question with no good answer waiting underneath all of it. Who do you call? Apollo 13 launched on April 11, 1970, and 2 days later, an oxygen tank in the service module exploded, crippling the spacecraft and placing 3 astronauts in immediate danger of dying before they could return to Earth. What followed has been described as NASA's finest hour, a masterpiece of improvised engineering conducted under extreme pressure, with the entire resources of the American space program mobilized around a single problem. Flight controllers worked continuously. Engineers pulled apart command module schematics at 3 in the morning, looking for power-saving solutions. A team physically built a carbon dioxide scrubber workaround, using only materials they knew were aboard the spacecraft, then talked the crew through replicating it. The crew survived. They splashed down safely on April 17, 1970. Apollo 13 was saved because the spacecraft was 3 days from Earth. 3 days. The communication delay was 1¼ seconds. Mission Control could talk to the crew in real time, assess the situation as it evolved, and transmit solutions within minutes of developing them. The entire infrastructure of human civilization was available immediately to solve the problem. Saturn is 7 years from Earth, not 3 days. 7 years. There is no version of the Apollo 13 story that ends with the crew alive if the explosion happens in Saturn orbit. The signal reporting the emergency takes 83 minutes to reach Earth. Earth's response, however brilliant, however rapidly assembled, takes 83 minutes to return. By the time Earth receives the first distress transmission and sends back even an acknowledgement, 2 hours and 46 minutes have elapsed. If the crew has hours to live, that exchange alone has consumed a significant fraction of the available response window. If the crew has minutes to live, the situation resolved itself before Earth knew it existed. A hull breach, a micrometeorite strike, a ring particle impact that was larger than the shielding could handle, a structural failure from 7 years of material fatigue depressurizes the spacecraft module in seconds to minutes, depending on the size of the breach. The crew has emergency procedures: seal the affected compartment, activate backup pressure systems, assess remaining atmosphere. These are actions that must be executed by the crew immediately, from whatever state they are in when the alarm sounds, with no external guidance possible in the time frame that matters. If the breach is large enough, or if the response is delayed by even a small margin, the outcome is death before Earth finishes reading the first automated distress signal. A failure in the carbon dioxide scrubbing system, the equipment that removes exhaled CO2 from the cabin atmosphere, creates a survivability window measured in hours. Carbon dioxide poisoning is not quick, but it is not slow either. At elevated concentrations, it causes headache, impaired judgment, and loss of consciousness in a progression that unfolds over hours, not days. The crew must diagnose the failure, identify the cause, and implement a repair or workaround using only materials present on the spacecraft, drawing on their own knowledge and whatever technical documentation they carried. No live consultation with the engineering team that built the system. No real-time troubleshooting with someone who has spent years understanding every failure mode of that specific equipment. Whatever the crew knows, and whatever tools they have, is the complete set of resources available. Medical emergencies represent a category of crisis that deep space planning has never fully solved. In 2014, ISS astronaut Karen Nieberg developed what appeared to be a potential dental abscess during her mission, a condition that, on Earth, requires a dentist and potentially minor surgical intervention. It was managed with antibiotics, but acute appendicitis, a condition that affects roughly 1 in every 1,000 people per year, and that requires surgical removal of the appendix within hours of onset to prevent potentially fatal peritonitis, has no antibiotic solution. A crew member developing acute appendicitis in Saturn orbit faces a situation where the treatment requires a sterile surgical environment, general anesthesia, and a trained surgeon performing a procedure that takes roughly 1 to 2 hours under ideal conditions. The spacecraft is not a hospital. The crew includes no trained surgeons. The surgical environment cannot be made adequately sterile in a habitat that has been occupied for years. The outcome of appendicitis without surgical treatment is peritonitis, sepsis, and death over a period of days to weeks. Earth can offer advice across an 83-minute signal delay. It cannot operate. Then there is the scenario that isolation research consistently identifies as one of the most difficult to manage: a crew member who becomes a psychological danger. 7 years of transit, months of operations in a radiation-saturated environment around Saturn, the physiological deterioration, the communication isolation. Any one of these stressors has demonstrated capacity to produce serious psychological breakdown in far shorter timeframes and far less demanding conditions. A crew member in a full psychiatric crisis, in a closed habitat with nowhere to go and no outside intervention possible, represents a threat to the entire mission and to every other person aboard. Restraint, isolation within the spacecraft, medication management. These are the tools available. None of them require a psychologist to implement. Because there is no psychologist, the crew handles it themselves, or they don't handle it, and the consequences of not handling it propagate through every subsequent decision the mission requires. NASA has stated this plainly in its Human Research Program documentation on deep space exploration risks. There is no rescue scenario for a crew operating beyond low Earth orbit at interplanetary distances. Any emergency that cannot be resolved by the crew using onboard resources and onboard knowledge ends the mission and the lives of the people on it. The agency frames this as a challenge to be addressed through crew training, redundant systems, and advanced medical capability, and those investments are genuine and ongoing. But the fundamental physics of the communication delay and the travel time cannot be engineered away. Whatever happens at Saturn, the crew is the only response that arrives in time to matter. The Saturn Mission Emergency Manual would be a remarkably concise document. Page 1, assess the problem. Page 2, solve it yourself. Page 3, if you cannot solve it, return to page 2. You survived. Everything that tried to kill you, the distance, the fuel mathematics, the radiation, the body's self-destruction, The psychological erosion, the ring passage, the capture burn, the orbital radiation belts, Titan's surface conditions, all of it, and you are still alive. The mission is complete. There is only one thing left to do: fly home. And this is the most dangerous part of the entire journey. Coming home after a long journey is supposed to be the easy part. The hard part is getting there. The hard part is doing the work. The return is the reward. The familiar roads, the known faces, the feeling of a place that fits around you, like something remembered. Every long expedition in human history has treated the homeward leg as the resolution, the exhale, the beginning of recovery. On a Saturn mission, the return journey is the most technically dangerous phase of the entire undertaking. Not the launch, not the ring passage, not the radiation belts. The last leg home, the part that feels like it should be over, is where the highest concentration of irreversible failure modes cluster together into a window measured in minutes, during which everything accumulated across 14 to 20 years either holds together or it doesn't. The spacecraft that departs Saturn for Earth is not the spacecraft that left Earth years earlier. It has aged in an environment that accelerates every form of material degradation simultaneously. 7 to 10 years of continuous exposure to deep space radiation has been working on every microchip aboard, displacing atoms in semiconductor lattices, accumulating charge in insulating layers, introducing subtle errors into electronic systems that have been operating and self-correcting against increasing noise floors for years. The metal structures of the spacecraft have experienced thousands of thermal cycles, expanding slightly each time they face the sun, contracting as they rotate into shadow, and metals subjected to thousands of thermal expansion and contraction cycles develop fatigue in ways that the original design specifications accounted for over a shorter mission lifetime. The rubber seals and polymer gaskets that maintain pressure boundaries throughout the spacecraft have been exposed to radiation that breaks polymer chains, making the material progressively stiffer and more brittle over time. A gasket that was flexible and compliant at launch may have the mechanical properties of aged plastic by the time the spacecraft needs to survive re-entry forces. The batteries that provide power during the phases when solar input is insufficient have gone through years of charge and discharge cycles. Their capacity diminished from original specifications in ways that compound as the cycles accumulate. Every single component on that spacecraft is older than it was designed to be for the mission's most demanding moment. The crew is in a parallel state of deterioration. The people who boarded the spacecraft at 30 years old, selected for peak physical condition, extensively trained, medically screened to eliminate any pre-existing vulnerability, have spent years in microgravity absorbing radiation and operating under chronic physiological and psychological stress. Their bones carry the density of much older people. Their muscles have atrophied despite years of mandatory exercise countermeasures that slowed the loss without preventing it. Their hearts have remodeled in response to years of operating without gravitational load, smaller and less capable than the organs that left Earth. Their vision may be compromised by the accumulated effects of spaceflight-associated neuroocular syndrome. These are not people at peak physical performance. These are people who have been systematically worn down by an environment that treats human biology as an obstacle rather than an accommodation. And these people, in this spacecraft, must survive atmospheric re-entry. A spacecraft returning from Saturn enters Earth's atmosphere at approximately 40,000 kilometers per hour. At that velocity, the interaction between the vehicle's heat shield and the atmosphere generates surface temperatures of up to 3,000 degrees Celsius, hotter than the melting point of steel, hotter than most metals used in spacecraft construction, hotter than the flame of an acetylene torch by a substantial margin. The heat shield is the only thing standing between the crew and that temperature. It is an engineered ceramic or ablative material designed to absorb and dissipate that thermal energy through controlled surface erosion, maintaining the vehicle's structural integrity and the survivable temperature behind it. For the few minutes re-entry lasts, the entry angle is not forgiving. Too shallow even by half a degree, and the spacecraft skips off the upper atmosphere like a stone skipped across water, returning to space with insufficient fuel remaining to attempt a second entry, leaving the crew in an orbit that decays over weeks or months. Too steep again, by margins measured in fractions of a degree, and the atmospheric deceleration forces exceed the vehicle's structural tolerance, or the heat shield experiences thermal loads beyond its design parameters, and the vehicle breaks apart. The corridor between these outcomes for a high-velocity return from the outer solar system is narrow. On February 1st, 2003, Space Shuttle Columbia disintegrated during re-entry over Texas and Louisiana. The cause, a piece of foam insulation, roughly the size of a briefcase, had broken away from the external tank during launch 16 days earlier and struck the leading edge of Columbia's left wing, damaging the reinforced carbon-carbon panels that formed part of the heat shield. The damage was not visible from inside the spacecraft. The crew did not know. The hole was approximately 15 to 25 centimeters across. When Columbia entered the atmosphere at the end of its mission, superheated plasma entered through that breach, destroyed the wing's internal structure, and broke the vehicle apart. All 7 crew members died. The heat shield on a spacecraft returning from a 14 to 20-year Saturn mission has spent that entire time in the radiation environment of deep space, absorbing particle bombardment that degrades material properties at the molecular level. It has experienced thousands of thermal cycles. It has never been inspected by anyone with the ability to repair it, because there has been no opportunity for external inspection since departure. A breach the size of Columbia's or smaller is invisible from inside the vehicle. The crew cannot see it. Mission Control, receiving imagery with an 83-minute signal delay, cannot assess it in any time frame relevant to re-entry decision-making. The decision to commit to re-entry is made on the basis of best available information, which is inevitably incomplete, about a heat shield that has aged in conditions no heat shield was designed for. You have traveled 7 years to reach Saturn. You have survived everything the Saturn system could produce. You have completed the mission. You are 7 years into the return journey, Earth filling the viewport, the home planet close enough that radio signals arrive in seconds again, close enough that you can see the continents. And the highest probability moment of catastrophic mission failure is the next 2 minutes of your life. Almost home is the most dangerous place this mission ever takes you. All of these risks, and we have not yet talked about the money, the ethical questions, and the reason robots do this better than humans in every measurable dimension that matters to science. NASA's annual budget runs at approximately $25 billion per year. The Artemis program, returning humans to the moon, a destination 384,000 kilometers away that humanity last visited in 1972, carries an estimated total cost of $93 billion through its initial lunar landing phases. The moon, 3 days away, a destination with no atmosphere, no radiation belts beyond the Van Allen transit, no ring system, no moons of its own, and a return journey that takes 3 days and has been successfully completed 6 times. Preliminary estimates for a crewed mission to Saturn, accounting for the propulsion requirements, the life support systems for a 14 to 20-year mission, the radiation shielding, the in-space assembly infrastructure, the Saturn operations phase, and the return produce figures that range from $500 billion to over $1 trillion. $1 trillion. For a single mission, NASA's entire cumulative budget across the last 40 years of operation totals approximately $800 billion. A crewed Saturn mission, under current cost modeling, would require spending everything NASA has spent on everything every Mars rover, every space telescope, every crewed mission to the space station, the entire shuttle program, the Hubble servicing missions, all of it, and then spending more on top of that for one expedition that may not return its crew alive. What does that expenditure actually purchase that a robotic mission cannot deliver? The answer, examined honestly rather than emotionally, is deeply uncomfortable. Almost nothing. Cassini cost $3.26 billion. It operated for 13 years in the Saturn system. It transmitted more than 600 gigabytes of scientific data back to Earth. It discovered that Enceladus has an active subsurface ocean venting water vapor and organic compounds into space. It mapped Titan's hydrocarbon lakes and seas in detail sufficient to identify individual drainage systems. It measured Saturn's atmospheric chemistry, tracked storm systems the size of continents, characterized the ring system in unprecedented detail, and returned approximately 500,000 images. It did all of this without eating, without breathing, without sleeping, without requiring psychological support, without developing bone density loss, without experiencing radiation-induced cognitive decline, and without needing a return journey. When Cassini's mission ended, the spacecraft went into Saturn's atmosphere. No recovery operation required. Dragonfly is NASA's next step at Titan, a rotorcraft lander capable of autonomous flight through Titan's dense atmosphere, landing at multiple scientifically selected sites, drilling into surface material, conducting chemical analyses, and transmitting results back to Earth. Its cost approximately $3.35 billion. It will do what a human geologist would do on Titan's surface sample collection: site survey, compositional analysis, without requiring a human being to survive the negative 179 degrees Celsius environment, without contaminating the surface with Earth biology, and without needing to come home. Dragonfly represents roughly 0.3% of the low-end cost estimate for a crewed Saturn mission and accomplishes the primary scientific objectives that would justify sending people in the first place. This is the number that reframes the entire conversation. A crewed Saturn mission costs approximately 150 times more than a robotic mission to the same destination. The robotic mission executes approximately 95% of the science that the crewed mission would achieve. The human presence adds emotional resonance, the possibility of real-time adaptive decision-making in novel situations, and the narrative power of a human being standing on another world. It adds the risk of killing everyone involved, the certainty of biological contamination of a scientifically pristine environment, and a price tag that makes the entire venture economically indefensible against any alternative use of the same resources. The contamination question is not a minor procedural concern. The human body carries somewhere between 38 trillion and 100 trillion microorganisms, bacteria, viruses, fungi, archaea, living on and inside it at any given moment. These microorganisms are not contained by spacesuits in any absolute sense. They shed from skin surfaces, travel in exhaled air, exist on every surface a crew member touches. Sterilization protocols that reduce contamination levels for robotic spacecraft protocols stringent enough that Cassini's final atmospheric plunge was partly motivated by preventing it from eventually crashing onto Enceladus. With residual Earth biology aboard, cannot be applied to living humans without killing the humans in the process. Titan and Enceladus are both considered high-priority targets in the search for extraterrestrial life. Enceladus vents material from a subsurface ocean that contains the chemical ingredients associated with living systems. Titan's complex organic chemistry makes it the most Earth-like prebiotic environment yet identified in the solar system. If a crewed mission deposits Earth microorganisms on either of these bodies through a suit breach, through surface contamination during operations, through any of the dozens of pathways that make human biological containment imperfect, and if those microorganisms survive and replicate in the local environment, then any subsequent detection of biological signatures on Titan or Enceladus becomes scientifically uninterpretable. We will never know if what we found was already there, or if we brought it with us. The question of whether life exists beyond Earth Perhaps the most important scientific question our species has ever asked would be permanently contaminated by our own presence. NASA's planetary protection protocols and the guidelines established by COSPAR, the Committee on Space Research, exist specifically because this risk is real and the consequence of getting it wrong is irreversible. If sending humans to Saturn costs 150 times more than sending robots, and robots accomplish 95% of the science, and human presence risks permanently compromising the most important biological discovery sites in the solar system, why would you send people? The most compelling argument for sending humans to Saturn is that the content would be extraordinary. First-person footage, real-time human reaction, the ineffable quality of a human being present at the rings of Saturn. The argument against sending humans is everything else: the cost, the contamination, the lethality, the redundancy, the sheer disproportion between what is risked and what is gained beyond what robots already deliver. After everything, the distance, the fuel mathematics, the radiation, the body's collapse, the psychological erosion, the ring passage, the capture burn, the radiation belts, Titan's toxic surface, the absence of any rescue, the death flight home, the money, you might think the biggest barrier has now been named. You would be wrong. 14 reasons. 14 distinct, documented, physically grounded reasons why anyone who goes to Saturn will never come back. Distance, fuel mathematics, deep space radiation, microgravity physiology, psychological isolation, a planet with no surface, a ring system that fires sand like bullets, a capture burn that cannot fail, an ISRU system that has never been tested, radiation belts that eat electronics and biology simultaneously, a moon whose atmosphere burns skin and whose surface liquefies everything familiar, no rescue possible under any scenario, a return journey through re-entry on a spacecraft older than its design limits, a cost that exceeds the entire history of NASA's spending. 14 reasons, and none of them is the real reason humanity hasn't gone. The real reason is deeper than any of those, colder, and considerably more unsettling to sit with. Everything described across this story, every barrier, every risk, every physical impossibility applies to Saturn. Saturn, which sits at 1,200,000,000 kilometers from Earth. Saturn, which light reaches in 1 hour and 20 minutes, traveling at 300,000 kilometers per second. Saturn, which is, in the context of the actual universe, not a distant destination at all. Saturn is in our backyard. It is a neighbor. It is the next street over in a city that extends, in every direction, for distances that make the word vast sound embarrassingly inadequate. The nearest star to Earth beyond our own sun is Alpha Centauri, actually a triple star system, with its closest component, Proxima Centauri, sitting at 4.37 light-years away, not light minutes. Light years. A light year is the distance light travels in 1 full year at 300,000 kilometers per second, approximately 9.46 trillion kilometers. Proxima Centauri is 4.37 of those. With the fastest spacecraft humanity has ever built, the New Horizons probe, which passed Pluto in 2015 and is currently one of the most distant human-made objects in space, the travel time to Proxima Centauri would be approximately 73,000 years, not 7 years, 73,000 years. Saturn nearly killed us. Saturn, which is 1 hour and 20 light minutes away. Proxima Centauri is 4.37 light-years away, and it is the closest star, the Milky Way galaxy, which contains the Sun and Saturn and every other object mentioned in this story, spans approximately 100,000 light-years from edge to edge and contains an estimated 200 to 400 billion stars. The observable universe contains an estimated 2 trillion galaxies, each containing hundreds of billions of stars, across a span of approximately 93 billion light-years in diameter. This is where the Fermi paradox acquires its sharpest edge. Enrico Fermi's famous question. Where is everybody asks why? Given the age of the universe and the number of potentially habitable worlds, we have not detected evidence of other civilizations. Many proposed answers exist, but consider this specific framing if reaching Saturn, which sits in our immediate cosmic neighborhood at 1 light-hour's distance, is already beyond the practical reach of the most technologically advanced civilization in our known history. Then what does interstellar distance actually mean for any civilization anywhere? The gap between stars is not 3,000 times the gap between Earth and Saturn. It is millions of times larger. If the physics that governs rockets and biology and human psychology make Saturn nearly unreachable, those same physics apply to anyone else attempting to cross the void between stars. The silence of the universe may not require a dramatic explanation. It may simply be what physics looks like at civilizational scale. The distances are not poetic. They are a wall. And yet the impulse persists, not just in aerospace agencies and mission planners, but in something more fundamental than institutional ambition. Why does humanity keep looking outward? Why does Saturn, despite everything, remain a destination? People dream about reaching. Why does the impossibility not extinguish the desire? If human beings cannot reach Saturn, and the universe extends billions of times farther than Saturn in every direction, then what does exploring the cosmos actually mean for a species confined, by the laws of physics as currently understood, to the immediate vicinity of a single unremarkable star on the outer arm of one galaxy among 2 trillion? Voyager 1 was launched on September 5, 1977. It has been flying continuously for 47 years. It is currently approximately 24 billion kilometers from Earth, the most distant human-made object in history, the farthest anything humanity has ever sent into the universe. 24 billion kilometers sounds, by everyday standards, incomprehensibly large. It is approximately 20 times the distance from Earth to Saturn. It represents 47 years of continuous travel at speeds no crewed spacecraft has ever approached. The distance to Proxima Centauri, the nearest star, is approximately 40 trillion kilometers. Voyager 1, after 47 years of uninterrupted flight, has covered approximately 0.06% of the distance to the nearest star. In the context of the actual cosmos, not the solar system, not the galaxy, but the universe as it exists, Voyager 1 has barely cleared the front porch of the house. We are not a species that conquers the cosmos. We are a species that has just learned to look out the window and is only now, for the first time, beginning to understand how large the house actually is